My name is Marko Hotti, and I'm Senior Solution Architect for Microsoft Data Platform. I am based in Finland, and I have been with Microsoft since year 2005. And before that, I worked for Oracle for 6 years. Basically, I have been involved with data warehousing, business intelligence, and mission-critical data platforms for over 20 years now. Today, I'm going to talk about SQL Server 2012 Parallel Data Warehouse, or PDW, which is the Microsoft solution for modern data warehousing and big data. I'm actually going to show you some demos later on, but before we go to the demo, I will talk a little bit about the traditional way of implementing data warehouses and why we need a new modern data warehousing architecture. So, the way traditional data warehouses have been built for many years is it usually starts from a business requirement. The business users want to have some kind of consolidated view over the business. They define requirements for the measures and KPIs, as well as dimensions they want to see in their reports and dashboards. They probably want to drill through to a certain level and maybe do some slicing and dicing of the data in their BI tools. And there is maybe an OLAP cube or some in-memory technologies like Power Pivot for Excel or analysis services, tabular mode between the data warehouse and the BI tools. But basically the queries against the data warehouse, they are pretty standard. Then we start a project. So someone starts modeling of the data warehouse, maybe choose between Kimball and Inmon models and so on, decide the data warehouse schema and so on. And then of course then there are the data sources that are required for reports, measures and KPIs. So we define and implement the ETL process. The data sources are typically ERP and CRM systems like SAP, Dynamics, Oracle applications, maybe some flat files and so on. Then the traditional data warehouse environment is planned. So someone needs to do the sizing of the data warehouse, decide about the storage architecture, what kind of disks and what kind of RAID levels and what kind of disk layout, what kind of hardware, how many CPUs, how many cores, how much memory and so on. And it's a pretty tedious task and it takes lots of time and planning and it's also costly. And it's usually based on the best guesses if you are not using any kind of reference architectures. And when the data warehouse has been implemented, so typically someone starts to optimize it using data warehouse technologies such as table partitioning, materialized views, index views, indexing, lots of indexing usually. All these things affect both the query performance but also the ETL load time. So there needs to be some kind of balance between what you actually want to do and implement in your data warehouse. Now, of course, Microsoft has all these great features of data warehousing in SQL Server 2012 Enterprise Edition, and SQL Server is very widely used everywhere in data warehousing. But maintaining and optimizing any data warehouse is a huge pain. And if we think about SMP architecture, so one single box, where we have one server with a certain capacity, we can only scale to a certain degree. Of course, there are the reference architectures and best practices to make sure that we can scale our data warehouse and you can optimize the data model and do things like that. And Microsoft has actually been working with different hardware vendors for many years to give guidance on reference architectures. So you have probably heard about Fast Track Data Warehouse and Fast Track appliances that we have been doing together with hardware vendors, and those have been around for many years, and those are great for data marts and things like that. The problem is the problem basically is this: there's a lot of new data coming all the time. The amount of new data is growing, and there is growing need for new data sources as well. A good example is, for instance, a manufacturing company who builds machines. So during the manufacturing process, they want to gather all sort of sensor and log data of the manufacturing process for future usage. They want to, for instance, see what happened during the manufacturing process, and to gather this information and store this information, they either use a traditional file system, or because it's for analysis and fast querying, so they decide to put this data to a data warehouse. And this is basically because, if this machine gets broken sometimes in the future, so they want to go back to the manufacturing process and to actually see what happened in the production line when they were assembling this machine. And this is kind of a typical big data scenario actually that I have been seeing a lot, at least here in Finland. And since data warehouse technologies are considered to be pretty expensive as to storing this kind of sensor data and log data to a data warehouse, they aggregate this new data, sensor data, log data, and this fast data in high volumes very heavily, so that maybe even 95 to 98% of this original data is thrown away and totally lost. And they actually put only maybe 3% of the original data as aggregated values to the relational schema, to the data warehouse, because data warehouses are pretty expensive to scale. So they are actually losing a lot of data, and this new data is really causing pressure to the data warehouse architecture and the solution. Another problem, I think, is the business users. They have new questions every day, and standard reporting and dashboards, they are not enough for these business users. They are not happy with the standard reports or the OLAP cubes, and they want to do ad hoc queries nowadays very typically and get new data sources quickly to their reports. And this new data can be from the processes that I mentioned before, but it can be also data from external new data sources. Business users usually have new expectations on the data warehousing solutions, and specifically ad hoc queries are something that they want to do. They want to analyze the root cause of why our business is doing and behaving like this, and why customers are doing this, and what kind of customers we could actually serve better, and so on. And they want to do market analysis and sales analysis and so on, and they want to get closer to the data. That's basically what the problem is. So it's about ad hoc queries, which are normally forbidden in traditional data warehouse. These ad hoc queries, they need to run really fast. And ad hoc queries are really difficult to optimize using indexing, because basically you would have to think about all these scenarios and create lots of indexes and do different kinds of other techniques in your data warehouse to make sure that also the ad hoc queries run smoothly. But at the same time, you compromise your ETL process and other things. And it's really difficult to maintain this kind of data warehouse. And of course, the data needs to be as recent as possible. So the ETL, the window, they can do ETL. It's getting more narrow all the time, and they really need to upload the new data to a data warehouse really fast, so that they can get very current results in their reports. So this kind of almost real-time reporting is nowadays kind of a requirement in data warehouse solutions. And then there are some solution areas also that are causing lots of problems in traditional data warehousing. And if we think about predictive analysis and data mining, so you really need to process huge amount of data to find the hidden patterns in the data. So a very common scenario, instead of analyzing business transactions, is to actually analyze what happened before the customer bought the product. So to analyze the conditions and what happened before the business transaction actually occurred. So this is what predictive analysis and data mining technologies actually can do for you. You can find these patterns. You want to find, for instance, what kind of customers are typically buying something, and then do customer segmentation, and then maybe suggest to a new customer that you look like you are typically buying bikes or cars or this type of products or books, and let's give you an offer or something. Or maybe like in this manufacturing case, maybe this company wants to have this kind of predictive maintenance solutions. So they want to actually gather all the data from the industrial internet, from the machines that they have been selling out globally, and then they get lots of data in, and they analyze this data with the predictive algorithms and data mining to actually predict when the machine is going to break down, so that they can be prepared when typically the machine needs maintenance. So predictive maintenance is one of the solution areas. So basically, data mining and predictive analysis in the SQL Server 2012 analysis services data mining capabilities, they can solve this kind of problems. You can use analysis services data mining to mine your data and then find these patterns, but you still need the data somewhere, and the queries need to be fast. So in the modern data warehouse, we still have the traditional data sources, SAP, Dynamics, Oracle applications, etc. And those data sources are usually best fit for a relational data warehouse as before. Processing of the queries, of course, need to be faster because of the ad hoc requirements, and it really would be great if we can do everything in parallel. So we want to utilize several servers and a huge amount of disks and spread the data automatically between all the servers and the disks, and process the data in parallel using MPP architecture. MPP means massive parallel processing, and PDW is Microsoft's MPP solution for data warehousing. There is also another technology which is MPP technology, and that's Hadoop. And what it does basically is it offers a file system called HDFS, or Hadoop distributed file system, which is like a very scalable file system that spreads in a Hadoop clusters to even thousands of data nodes. All the data coming from devices, web logs, sensors, etc. are simply stored as they are in the Hadoop file system, and you can scale easily because Hadoop supports this kind of scaling out by adding cheap hardware and disks to the cluster, and that's basically how this Hadoop file system is implemented. Hadoop will slice the incoming data in small chunks and make copies of these chunks to several data nodes, so it also makes the data very redundant. So it's a resilient file system. In Hadoop, however, we don't have a schema when we write to the file system. So if we compare to traditional data warehousing, where there is always the schema, the tables and columns and relations where we write the data, in Hadoop we don't have that. We just put the files in HDFS and create the schema or the structure afterwards based on what sort of data and structures we want to get from the files. And this process is called MapReduce. It's part of the Hadoop architecture, and it usually requires a lot of coding in Java or using other Hadoop interfaces such as Hive or Pig. This makes Hadoop very complex to use, and there's a lack of Hadoop competence in the world because of this complexity of Hadoop. But basically, it is a cheap and scalable file system optimized for fast writing and parallel processing of the data in the files. But because of this complexity and different kind of technologies and lots of programming and coding projects and so on, so it's really difficult to find people who know Hadoop and who can write the MapReduce code. And it's also because it's open source, basically built on different kinds of projects and so on. So maintaining a Hadoop cluster is actually pretty complex thing, and even deploying a Hadoop cluster can be a complex thing. So that's why there are distributors like Hortonworks and Clouder and so on who make Hadoop packages which make it a little bit easier to deploy Hadoop in the data center. And this is why Microsoft is also partnering with Hortonworks to actually have a Hadoop solution in the cloud. So HDInsight in Azure, Windows Azure, is our Hadoop technology. So in the modern data warehouse, we want to have a flexible architecture, and for that kind of data, which is originally non-relational data coming from devices, web sensors, web logs and sensors and so on. So we can store that data into Hadoop and use Hadoop simply as a scalable and cheap file system. And in parallel data warehouse, we have a technology called PolyBase. And this is a great technology, and it's really, really great. I will show it to you in my demo. But what it does basically, it automates the process of the Hadoop MapReduce process. And so it generates actually code that is run against your Hadoop cluster. And you can actually handle, query, and process the Hadoop data using your SQL Server skills. So you don't really have to learn how to write MapReduce. Hadoop data looks like any relational table in your data warehouse, and when you query that data, PolyBase will create the MapReduce process and query the data directly from the Hadoop data nodes, which are storing the data. So for instance, if there are like 50 data nodes in your Hadoop cluster, so PolyBase will run fetch the data in parallel from all these data nodes and process it very fast, and then you can read the data through the PolyBase tables. And it's really much faster than Hive technology, because in Hadoop there is a thing called name node, which is normally used for doing submitting the MapReduce tasks and to control the MapReduce process using the job tracker. And what it does basically is that when you run the native Hadoop MapReduce, so the data nodes will spread the MapReduce code on all the data nodes in the cluster. Those clusters will structure and slice and dice the data, and then you get the query results back to the name node, which is like under lots of memory pressure and processing pressure at that point. So it's really becoming a bottleneck in the Hadoop architecture. And then after the query result is ready, so data node will give you it will sum up the query result, and then you can get answers from Hadoop. But PolyBase does this differently, so it queries the data nodes directly. And I will show you PolyBase later in my demo. So PolyBase is the technology behind the integrated query model. So you can join Hadoop data such as sensor and log data with traditional relational data coming from ERP and CRM systems. And you can do this with your existing SQL Server skills, like I told you before. And then of course Microsoft has a great stack of BI tools, and those are like Power Pivot for Excel, which gives the business users the possibility to do self-service in-memory analytics of the data, so they can connect to one or several data sources like parallel data warehouse and external data sources, and join this data in memory in Power Pivot, and then start analyzing and visualizing the data using the Excel interface. In SQL Server Analysis Services, we have, of course, the OLAP cubes and in-memory analysis technology as well, called the Analysis Services Tabular Mode. We have data mining and predictive analysis algorithms in Analysis Services, and you can also use the data mining add-in for Excel to experiment with data mining. So, for instance, if you want to test different kind of data mining scenarios, so you can extract some sample data on your Excel spreadsheet and then test different kind of scenarios using this data mining add-in, which is a free tool, freely downloadable from Microsoft website. And then there are other features such as Power Query for querying external data sources such as social media, OData, websites, and so on. Power View, which is great for doing ad hoc reporting in a web browser on SharePoint platform, and also nowadays it's embedded in Excel 2013. And then we have Power Map, which is for location data and business data. So, for instance, if you have like some business transactions and you know where your customers are, so you can actually visualize everything on a three-dimensional map and be interactive with your data and see where your customers are or what's happening and where are the hotspots and so on. So lots of BI technologies and all these are evolving all the time. Hadoop is very easy to deploy if you get it from Windows Azure. The Microsoft Hadoop is called HDInsight, and like I told before, so we work together with Hortonworks to provide this. And you can also use your on-premise Hadoop built on Cloudera or Hortonworks data platform. So there are lots of different options. You can run Hortonworks data platform also on Windows Server, so not only Linux. And we have been hardening the Hadoop technology with Active Directory integration and System Center integration. So Hadoop is now really enterprise ready for serious use. From the modern data warehouse point of view, we optimize the scalability by storing different types of data in different types of storage. So either we store the data from traditional data sources, relational data sources inside PDW appliance disks and the actual data warehouse tables, spread it across all the nodes and all the disks that there are within the appliance. Or you can use Hadoop, and usually customers want to use both because they both have, like, you know, the flexibility and the performance, but also depending on scenarios. So maybe you want to upload your data first to Hadoop and then move it to PDW, to real relational tables. PolyBase is the bridge between these two very different worlds, and it gives you the seamless integration, and you can actually move data between PDW and Hadoop. So one good example is that once you have like lots of sensor data and log data in Hadoop, so you can extract interesting data from Hadoop using PolyBase and put the data to your relational store within inside PDW. And but it also works the other way around. So for instance, if you have a very big data warehouse, you have lots of transactions, facts about, you know, business transactions there, and you have several years of data in your data warehouse, and you know, normally the analysis is focusing on maybe the last 5 years and so on. So the older data is actually taking up the storage and the capacity of the data warehouse. So what you can do is basically you can move the old data, old partitions of your data warehouse to Hadoop and push the data through PolyBase to Hadoop, where the data is then on a cheaper architecture because Hadoop is cheap, but you can still query that data also because it's online and you can access that data through PolyBase. So it gives you lots of different kinds of flexibility scenarios, flexible scenarios in data warehouse maintenance. So a quick slide about comparison between SMP and MPP. I have been talking about this already, so you basically know about this, but SMP is basically one piece of hardware, like, you know, maybe 4 CPUs and 92 gigabytes of RAM and certain amount of disks, and you can really only scale up by buying a new hardware, and that's the only way of scaling up the data warehouse based on SMP architecture. And it's really difficult to predict the performance of SMP if you have future workloads, and ad hoc queries are normally totally forbidden in this kind of architecture. But it's still a very good data mart solution, for instance, in a hub and spoke architecture with SQL Server PDW. So you can use, for instance, SQL Server fast track appliances, or even, you know, plan your own SMP environment in a virtual machine with SMP architecture. That's totally okay. But the real processing power and the real scale out comes from MPP appliance, PDW. So you can start with a quarter rack with a couple of servers and disks a certain amount of disk storage, and when you grow, when you get new data, so you can scale by buying new hardware inside the rack, so you get half rack and then 3/4 rack and then full rack. And once this one rack is full, so you can start putting new hardware to a second rack. So you can scale out really by adding new servers and new disks to this appliance. And PDW actually scales out to several appliances and up to 6 petabytes basically. So it's really a scalable solution. This kind of modular approach is really great, because you don't really need to replace your appliance when you get new data and you need more performance, or you have new business requirements for your data warehouse. So you just scale by adding new servers to the rack and then new disks to the rack and so on. And it's really a big data appliance in the sense that you can store any kind of data and you can access any kind of data using PDW through PolyBase. And since this is an appliance, so it's really fast to deploy. You get it from the factory, and you just bring it to your data center and plug it in and connect it to the network, and our technician will come in and make sure that everything is running smoothly. And then you start creating your data warehouse tables and start loading your data, and that's it. And there is also built-in high availability architecture, so that it makes sure that when there is problems with the disks or servers, so it will automatically fail over to some other server and so on. So it's a great solution for that. So it's based on distributed architecture, massively parallel processing architecture with many physical servers, and and there are so-called compute nodes that run all the queries in parallel against distributed data that is spread across the appliance. So that's one thing. And then there is a control node, which is the brain of the PDW. And what it does, it basically accepts the user queries, generates the execution plan, and distributes the operations in parallel to compute nodes. And then there is also a management server that makes sure that all the components, disks, servers, operating systems, and so on, they are working okay. And it takes care of monitoring of the appliance and gives you the health status of the appliance, and also take care of those administrative tasks like patching and things like that. So it's really like the healthcare center of the appliance. And we currently deliver it together with Dell and HP. And there is a single call support, so even though this is like for instance HP and Microsoft offering, so you really get the support from one place, and that's Microsoft. And something about the technologies that we have in PDW. So this one is very important. The in-memory column store in PDW is very important technology, and if you use it in your data warehouse tables, basically all the data in the table is organized in the disks in column segments, column-wise, and it will be also compressed. So we are not using a row store at all. So column store technology means that when we do a query of a table that has this column store technology option, so we only get those column segments from the disks that are required to give the query a result, and we don't touch the other data of the table. So let's assume that you have tens of billions of records in your fact table, and you have like 40 columns in your table, and in your query you are only aggregating you are querying only 2 columns of that table. So we only touch those 2 columns and only fetch the column segments of those 2 columns from the disk that we need. So we don't touch the rest of the data of those tables. And Since it's compressed column-wise, so it really has huge impact on query execution time and the amount of time it takes to do aggregations and other calculations based on column values. So it's really great technology to speed up your ad hoc queries. And column store tables, which are always also called clustered column store indexes, they are updatable. So you can update those tables. There is an internal mechanism to make sure that you can load data fast to these column store tables without affecting the query performance. Another important technology in PDW is the way we distribute the data between different compute nodes and huge amount of disks. And the distribution technology is very interesting, and it's very important as well. If you choose to use distributed tables, so the table will be kind of automatically hash partitioned across the appliance. It is not really hash partitioning, but we simply pick one of the columns in the fact table that we use as the seed value for the hash algorithm, and then based on the hash algorithm result, we decide into which distribution we put the row. And there will be 8 distributions per table per compute node. So in my example, for instance, in my demo environment, we have 8 compute nodes, and there will be 8 distributions per compute node. So each and every distributed tables will be distributed in 64 different distributions across the appliance, so that all the data will be evenly laid out on the disks. And when we query the data, so we are actually consuming all the power of the appliance in parallel evenly, and also the data will be spread evenly across the appliance and all the disks. So it's really great technology, and it's best fit for huge fact tables where you have like tens of billions of transactions, fact data. The other option is to use replicated tables, and that's by default. So when you create a normal table in PDW, so it will be replicated. It has nothing to do with database replication, but it simply means that we keep kind of a synchronized copy of the table in each compute node, so that there is a copy of the same data in each of the compute node. And the reason why we are doing this is that when we do query, and for instance, if we join data between a distributed table, a fact table, and then dimension tables, which are usually replicated tables, so we can optimize the disk I/O by fetching the relevant dimension rows and also the fact table rows at the same time with the same I/O, and then process the data. So these are the two things. It's either replicated table or distributed table, which is great for fact tables. And of course, I will be showing you all these soon in my demo. And I already told you about PolyBase, so I'm not going deeply into this, but just to sum up, so it's the bridge between the Hadoop world and between the relational. And you can use Hadoop as relational tables. They are called external tables, and when you create a table, you define how you want to do the map reduce by defining the structure of your external tables, and PolyBase will take care of the coding and fetching the data directly from the data nodes. And so Hadoop for you would be just a file system, scalable file system, and you don't really need to worry about how to do coding in Hadoop, and you can use your SQL skills. And of course, there is no IT intervention, especially if you deploy Hadoop in Windows Azure in HDInsight. So it's really easy because Microsoft takes care of the maintenance of the Hadoop cluster and so on. So you really save time and costs. And this gives you the flexibility of storing all kinds of data in the modern data warehouse. Okay, I think I have been talking enough, so it's time to show you a demo. And so I will show you all these technologies in parallel data warehouse, like in-memory clustered column store or the column store tables, distributed tables. I will load data to PDW with DW loader, which is a DW loader, which is command line tool for directly loading data in your flat files, for instance, to PDW appliance. I have some demo databases where for example, I have 10 billion rows of fact sales data, sales transactions, and I do ad hoc queries against this kind of data warehouse and database, and I show you different kind of queries, and then of course I show you the PolyBase. So that's about the PowerPoints, and now we go to see the demo. Okay, so let's start with the demo. Before I go to the PDW appliance with my remote desktop, so I will just briefly show you Windows Azure. This is the management portal for Windows Azure, and as you can see, so here we have HDInsight, which is the Hadoop in Windows Azure that we do together with Hortonworks. And creating a Hadoop cluster that you can start using is really easy. So I just give the Hadoop cluster name. Let's say Marcos Hadoop cluster 1, and I tell what size of cluster I want to have. So let's say I want to have 4 nodes. I pick that, and then I confirm my admin password like this, and I give a storage account, and then I click create, and now Windows Azure starts to deploy a Hadoop cluster, which is 100% open source compliant, following all the Hadoop standards and so on, and you can start uploading your data to the Hadoop file system later on. And I have actually Hadoop cluster here in my demo, so I'm not going to wait for this to complete. I just go directly to the demo. In my demo environment, so I'm going to show you first, let's say, one scenario, which is loading the data. So what I have here is I have a database. I have PDW demo _ Marcohot, and I have created a database with this kind of options. And if we think about traditional data warehouses, so when you create a data warehouse, so you really need to do proper planning. You need to know where you want to put your data files and how to spread the data files across all the LUNs, logical disk units in your environment, and you need to give different kind of parameters and so on. And you also need to decide where you put your temp DB and where you put your log files and so on. With PDW, everything is done automatically based on best practices and reference architecture. So basically all you do is you give the create database command, and you tell a couple of things. You tell the initial size for distributed tables, and initial size for replicated tables, as well as initial size for logs. And then you tell I want to have outer row on, so it will then, let's say distributed size now is 1 terabyte. So when we reach that limit, so PDW will automatically extend the storage space to accept new data, and you really don't need to do anything else. So it's pretty easy, and I have done this already, so I'm not going to do it again. So then I'm going to show you a demo about data loading, and I'm actually loading receipt lines from a flat file. That's one of the scenarios that we usually demo, and how fast it is to load data to the appliance. And for data loading, we are actually using the internal InfiniBand, which is 56 gigabit network inside the appliance. And you can connect your SSIS or your ETL tool to the appliance using the InfiniBand, so you really get the good performance of the network. Here is the create table clause that I'm going to use. So I'm creating a table called line item underscore CCI, stands for clustered column store index, and I give the definition of my table. So I have order key, part key, supplier key, line number, quantity, and so on. And this is pretty regular stuff as you would do in normal SQL Server, but this line here is very important. I'm telling that I want to organize all the data that goes into this table in column format, in the column store, so that each and every column will be stored separately in the disk and spread out, and it will be compressed. And the other option that I give is distribution. So I want to have a distributed table. So like I told before, so there are two options. You either make replicated tables, which is the default, or you define that you want to have a distributed table. And here I'm giving one of the columns as hash key. So I'm using the order key value to hash the data into different distributions. And since my environment is 8-node PDW, I'm actually going to show you later on what's happening inside PDW. So there will be 64 distributions per table here. So let's run this command. Sorry, I didn't realize that I probably had already created some tables during my previous demo, so I'm actually going to delete these tables before I do this. Okay, so let's start again. Create table and execute. So what we have now is the line item table here, and I just refresh so you see that now the table is over here. We can use a command called dbcc pdw underscore show space used to see how the distribution works. So initially this table is empty, of course, because I don't have any data here. And here we see lots of useful information. We see the amount of rows per distribution. Here we see the node name, so will be or node ID. So there will be 8 nodes since this is a 8-node appliance, and each and every node has 8 distributions. So let's start loading the data, and for that I'm using the DV loader tool, which is basically loading all the data from a flat file called lineitem.tbl to appliance, and I'm telling in this command line that I'm going to load my data into the this table here. So I copy this command just to make things a little bit easier. I'm using the InfiniBand. So InfiniBand is the fast network inside the appliance, and it's really good for data loss and SSIS, but it's also guaranteeing the performance inside the appliance. So all the nodes inside appliance are communicating using the InfiniBand. So I start the command. So I paste my command here and start loading the data. So it will start processing the file and inserting the data directly to the table, and we see that now we have already uploaded like 8 million rows. And what we can do now is we can actually monitor what's happening inside the appliance. So what we can do here is we can go to a PDW admin console, which is a web-based tool for doing for monitoring about what's happening inside the appliance. So this admin tool gives me insights about the sessions that I'm currently having inside the appliance, what sort of queries we are running. You can actually actually see the execution plan of the queries and see what happened and how the query was behaving and what sort of paths we were using in that. So then we have loads here, and as you can see, I'm clicking here and I see that I have currently one running load process going on, and here is my command. So here you can see that I'm loading data, and currently I have loaded and inserted 96 million rows, and the duration of the load is currently 1 minute. So okay, there will be 6 million rows, so it will take a couple of more minutes probably. In the meantime, we go to see some other things. So here you can actually see what's inside the appliance. So we have the control node, we have the 8 compute nodes, and the management node, and the status is healthy, like it should be. And the performance monitor is a good way of seeing what's happening inside the nodes, what's happening in the disks. There are lots of different kinds of graphs that you can get from here if you want to monitor the network interfaces or data movement services or some other things. So you can do that using this tool. Right now we are not going to deep dive into this, but we see that we are actually generating load into several nodes, so it's probably a good thing because we want to use the MPP capabilities of the appliance. So while we are loading the data, so we are actually starting the PolyBase demo, and for that I first show you Hadoop. So in my Hadoop cluster I have actually 3 data nodes. This interface is standard Hadoop interface. So there are command line tools, of course, but then there is also this website where you can do different kinds of things. So you can see, for instance, the nodes that you are having in your Hadoop cluster, and in this case I have 3 data nodes: HDP2, HDP3, HDP4, and so on. And I can also browse the file system, so you see that there are different kinds of directories here. There is a user directory, and there is actually a directory for myself called Markohot, and it's currently empty. And we can also query Hadoop using the command line, which is I'm actually going to use. So for instance, if I want to see the file system, so I give the command Hadoop with the FS option, and then I give this kind of Unix type of commands like ls for listing the directory contents. So I give my directory, and as you can see, so it's empty. And I'm going to copy some data later on to this directory, so you see how PolyBase works. Let's go back to my tool here, and let's go to this part. So what I'm now going to do is I'm going to create external tables, which are the PolyBase tables. So I first show you that we don't have any, we actually have some tables here already because I did this demo just recently. So I'm going to actually delete these files, so that's we can start from 0. So I delete these tables and I run this query again. So just a second. And now we see that we don't have any PolyBase tables here. So creating a PolyBase table is pretty simple. So you just create table, but with the external option. So you tell create external table, then you give the table name. And in this case, I have some tweets in Hadoop, and so there is some data about tweets about different kind of data car models and car brands. So I create a column for tweet, so the actual content of the tweet, then a column for tweeter name, tweeting date, and then the car model that the tweet is about. And this is the important part. So I tell where my Hadoop cluster is. So I tell the address of my Hadoop and also the directory where I'm going to retrieve the data from. So So I will have this directory later on in my demo, and then I give format options, which is basically deciding how to structure the data in the files. So I give field terminator and so on, string delimiter and different kind of options. And there are different kinds of ways of doing this, but this is a very simple scenario. So I create this, or I try to create this table now, and as you can see, so it will give me an error because I don't have this directory yet here in the Hadoop. So I go back to my Hadoop and I actually copy the data from a demo data store that we have here. So I give the command Hadoop fs for file system, and then put, which is for copying data, and then I give the source directory, which is cars data, and then the target, which will be Marco cars and data. And with this command, so there will be now data here. And so if I give this command again, so you will see that there is actually now this directory here, and we can see the contents of this directory now. So you see that there are text files here, and these are the tweets in file format. So this could be like sensor data or weblog data or any kind of unstructured data or semi-structured data that you just store in Hadoop file system and reuse later on using PolyBase. So the next thing is I try to run this query again. So now it should go through. So as you can see, command completed successfully, and now I can start using this PolyBase table or this external table just like any data warehouse table. So I can do select. So now PolyBase will generate the MapReduce code, fetch the data from all these 3 data nodes that I have in my cluster directly, and then give me the answer. So looks like okay, the query works. I can do things like select newest tweet first. Sorry. Or I can, do different kind of queries like show brands, models, tweeters, and number of tweets. So it will give me good results. What I can also do is I can move data from Hadoop to PDW. So for that I'm actually doing create table as select. So I create a table called tweeter, which is a normal distributed table inside PDW, and I create that table by selecting data from the Hadoop table car tweets. So now I give this command, and as you can see, so it works, and now I can query that data. So this is very useful for if you have lots of sensor data or whatever, and you are interested in certain type of data in Hadoop, and you reuse it frequently. So it makes sense to move that data into the appliance to reside actually as a probably column store data and as distributed tables, so that you can really process that data fast, because there's always a little bit of latency when using Hadoop tables. And what I can do, of course, now is join the internal data and external data. So let's think that you have SAP and or CRM data in your data warehouse, and you want to join that data with some weblog data to analyze something like what your customers have been doing in the website. So joining that sort of those 2 types of world makes sense, and so it works very smoothly, and it's standard SQL. And I got results. So this query returns the number of tweets per car model. So how many cars were mentioned, how many times Renault Megane was mentioned, and so on. And what I can also do is I can export data from PDW to Hadoop. So this one is create external table as select. So I create a Hadoop table. So I create external table, and I tell the location of my directory where I want to put the data onto in Hadoop. So I give my a Hadoop cluster address, and then the directory where I want to put the data, and it will then reside in Hadoop, and I will show it from the Hadoop side then how it looks like. So now the data was exported to Hadoop in the file system, and obviously if I go here on Hadoop side and I give the command Hadoop fsls user marcohot tweeter, so now we see that we have text files here which are automatically generated with the create external table as select. So this is how PolyBase works, and I think our data load has already finished. So let's see what's happening here. Yeah, all the 600 million rows were processed, and if we go to the web admin interface, so we can go to the loads section and see actually statistics about this. So here is my load process, and here we see that 600 million rows were inserted. The status is completed, progress 100%, and here we see the duration of the load. So it was 5 minutes 27 seconds, which is pretty consistent result. I got this last time as well, and probably the column store compression has a little impact on the performance. So if we don't have column store, so it might be even a little bit faster, but I really want to run ad hoc queries to my table, and I think that column store is a good option for my table. So I want to do column store. And just to check what kind of data we have here, so we can actually now before we do the query, so actually I show you the distribution of the data. So I run this dbcc pdw show space used once again, and as you now see, the distribution works really effectively. So we have the 64 distributions, 8 distributions per compute node, and as you can see, in each and every distribution we have something like 9.3 million rows. So the data of this table has been spread out very evenly across all the nodes and disks, and it's easily accessible, and the performance will be really good when I'm querying this data. And so let's try just one simple select. I do some aggregations here, summing, some calculation, average, and so on. I'm counting the order numbers, the number of orders and so on, and I do some grouping and ordering of the query result, and I run this. So let's see what happens. So it will now execute the query. It gave me 4 rows, as you can see, and the query execution time was 3 seconds. So pretty good. I'm not complaining. Let's go to another database which I have here for demo purposes, and that's the demo DB CCI table here, or database here, which is more relevant maybe to real-time scenarios or real-life scenarios. So it is actually a data warehouse with dimension tables like customer, date, product categories, product subcategory, and so on. And we have fact tables here. So for instance, what we have here is fact sales 10B, and this table has basically 10 billion rows of sales transactions. And to prove you this, so I'm actually going to show you. Let's do select count big from fact sales 10B. So you will see that that's 10 billion rows really. And let's see what kind of data we have there. So select top 10. Where is my from fact sales 10B, and we'll see what kind of data we actually have there. So it has online sales key, date key, store key, product key, and sales order numbers, and some quantities, sales amounts, and so on. So pretty typical sales data, sales transactions that we have here. So let's try first finding the minimum and maximum value of sales order number. So basically this one is a very heavy operation in SMP architecture, because you really need to fetch all the rows from the disks first, and then you need to find the particular column that you are interested in, and then you need to sort the data and then find the minimum and maximum value of this. So in SMP architecture, this would be really a heavy operation, and it would take a lot of resources in the server. So I'm going to run this query now, and it will take some time. So let's go to the performance monitor, and here you can see that that we are actually using several compute nodes in finding the results, and we are reading actually disks here. So if we take a look at, let's say, compute node 4, and we want to see what's happening here. So okay, we don't see much action anymore, because actually the query probably ended. So it was executed, and we see that there is no load anymore. But if we go back to here, so you see that okay, we got the result. We found one row, or it gives me one row, and it took 39 seconds. So it's pretty good. And the reason why the performance is so good is that we are using the clustered column store. So we are only picking the sales order number data from the disk, from the distributed table, and so we are not touching the rest of the table at all. And to see the distribution, so let's do PDW show space used here, and here you see the similar behavior that we had in the previous example. So 64 distributions altogether, and each and every distribution has something like 157 million rows. So pretty evenly spread across the distributions and compute nodes. So this is the technology behind the MPP processing. Let's try a couple of queries. Here is query 1. So we want to see the sales per product category, current year versus previous. So it's not very complex query, but it takes some time to process. So let's see how this one works. So I execute this one, and it takes some minutes, some seconds. So it took 4 seconds to execute, and it gave me 32 rows. And now I see product category, product subcategory, and then aggregations, sales amount in those 2 years. Pretty good. Another query, top stores and products and total sales ranked. So here we are actually joining some tables, and we are also calculating sums, and we are doing ranking. And this one is also a little bit complex in SMP architecture and difficult to optimize using indexing. It's doable, but it would still be pretty slow. And in PDW it took 4 seconds, and it gave me 30 rows. So very good results. The third query, that would be basically calculating sales amount, cost and profit per state province name, customer type and calendar year. So we see we are doing summing here, and we are joining some tables, and we are grouping data, and let's see how this one works. So this query also returns the result pretty fast. It takes a little bit longer than the previous queries. It took 9 seconds, and it gave me 740 rows. And the fourth query, which is also the last query that I'm going to show here, that's a long one, and it doesn't actually fit in the screen. So we are selecting store, product name, we are calculating total sales, rank results, and then we are also getting total sales for the years 2010 and 2009. So this has subqueries here, and we are doing quite a lot of complex joins here and calculations and so on. And let's see how this one works. Okay, and we execute this, and so now we probably see lots of action here. Yes, we are reading data, but now it's not doing much anymore, so probably the query also ended. It was executed, and as you can see, so this very complex query, it took only 10 seconds, and it gave 300 rows, so pretty impressive results. Okay, so that was basically my demo. So I just shortly gave you an idea about how to deploy Hadoop in Windows Azure as HDInsight. It was a 4-node cluster. I showed you how to load data using DW loader to a clustered column store table or clustered column store index to a table which was distributed. And then we did some PolyBase stuff, so we had data in Hadoop file system. We copied data there and then created PolyBase tables and queried the table, and then moved the data between Hadoop and PDW. And then we did some complex queries against 10 billion rows of sales data. So that was about my demo. If you have any questions, so please don't hesitate to contact your local Microsoft contact, or you can also send email to me. But of course, if you are international audience outside Finland, so you probably already have a local contact in the local Microsoft organization, maybe a TSP for data platform who is responsible for BI or data warehousing. So you can contact him or her as well. Anyway, that was it. Thank you for listening and watching. Have a nice day.